Hello and welcome to our flip clip today, guys and girls, on how plates move. Here's our plan. We're looking at how plates move. We've got two different ideas here. One, we think they might move by convection currents in the asthenosphere, or two, we think they might move by the action of gravity, creating a ridge push and slab pull on both sides of an oceanic plate. Now that might sound like gobbledygook, but by the end of this video, you need to be successful when you can explain both of those theories, one, convection currents, and two, ridge push slab pull, illustrating your understanding with a labeled diagram. It's actually a really important idea because it gives you an example of science hasn't figured out all of the answers yet, and this was one of the main stumbling blocks that Wegener had. He thought that all of the continents had moved in the past, but he didn't know how they had moved. So now that we have those two different ideas about how they move, we both think that they're both equally likely, and probably this number 2 here is a tad more likely in the modern literature. That really separates a modern theory of plate tectonics from that original idea of continental drift. But first, you need to remember the layers of the Earth. Here we have a diagram that looks like it's been drawn by a chimpanzee in paintbrush. Actually, I think it does look like it's been drawn in paintbrush. This is what you will have learned in year 9, and we did it earlier this year, and it's not quite good enough anymore. This is a diagram that looks like it's been drawn in some sort of terrible textbook and then scanned in badly, but it gives you a whole lot more information. We still have our inner core, our outer core, mantle, and crust. But here is some other information that this diagram gives you. 1. The mantle here is made up of its own distinct layers. Importantly is the word asthenosphere at the top there. There is your definition. I'll get you to come and write that down after when you draw yourself a diagram, because we need to know that the asthenosphere is the upper layer of the mantle. It flows very, very slowly. Something else that this diagram shows us is we've got some crust over here that have mountains, so this section there, and that makes up the continents, so we call that continental crust. This section of crust over here beneath the oceans is called oceanic crust. And the main difference from that diagram looks like the oceanic crust is just thinner, and therefore it has water on top of it. So let's focus in on that asthenosphere. The asthenosphere is sort of a little bit like the ocean. If you think about the ocean has waves, think about that there are boats that sail on the ocean. There we go. That's me, my yacht. When the ocean moves, the boats move. That's pretty simple. So think about it this way. The asthenosphere is that upper part of the mantle, so that is like a liquid hot, super duper slow ocean. The plates are the boats that float on top of the asthenosphere. Just like when the ocean moves, it moves the boats. When the asthenosphere moves, it moves the plates. Question, you might think that it's a bit funny that crust is like the land and that actually floats on this asthenosphere ocean. Well, that's because the crust is less dense. And you'll remember from the very, very beginning of the year when we were talking about differentiation, you remember that the layers of the Earth settled out because of their density. Inner core, most dense, less, all the way to the crust at the very edge, which is the least dense. So that's why I say the crust actually floats. The main idea here is what we call convection currents. The asthenosphere moves in currents, just like the ocean. The crust gets pulled along because the crust is floating on top. Now, I know I was making fun of drawing in paintbrush before, but I made you this animation, so don't make fun of it. It shows you convection currents, so I'm going to hit play. The convection currents are hot down the bottom, heat rises, comes to the top, splits off, goes to the side, gets cool, turns blue, comes back down to the bottom, gets hot again, goes back up. I'll play that one more time for you. And voila. The idea behind the convection currents is that heat rises Again, from when we did density, it's because hot things are less dense. To summarize, the first theory is convection currents. Main ideas being plates float on slowly flowing asthenosphere. The asthenosphere moves in convection currents because hot things rise and cool things fall. And the plates that are floating on the asthenosphere move along too. Okay, theory number 2. So before we push on to the next theory, I just wanted to outline why. Why is it that hot things rise and cool things sink? And this goes back to particle theory that you would have done maybe in year 7. So that was a while ago. You would have learned about solids and liquids and gases, and how when things get hot, like when you boil water, the ice melts and all the particles here jiggle, and then they turn into a liquid which flows. All the particles here move out a little bit and they're flowing a little bit more over here. And then eventually you boil the water and it turns into a gas and it disappears because the particles shoot off into the room. That's literally one of the first things you do in year 7. In that little box there are 16 particles. 7 over there and 3 over there. So we say that that box represents 1 cubic centimeters. So in the solid it has 16 per cubic centimeter, 7 per cubic centimeter, and 3 per cubic centimeter. Looking at that, this is our differentiation all over again, everyone. The most dense things sink, 16 particles per cubic centimeter is the most dense at the bottom. And then as things become less dense, they rise. You're making the connection now. The hot Bunsen down the bottom is what's causing the particles to spread out. Hot causes them to become less dense, and that's why they rise up. Say that one more time for clarity. The hot causes the particles to spread out. That causes them to become less dense, and that's what causes them to rise. And that is why we have the layers of the Earth, the most dense ones, at the inner core, outer core, and then mantle and crust. And here we are. We have a picture of a mid-ocean ridge. It's underneath the ocean, and the ocean floor is cracking and spreading. We can explain that via convection currents, just like I did before. That movement on either side because of the convection currents pushing the floor apart. But if we take a zoomed out view, this is what we see. Now I know I'm giving it away because that one's labelled, but what I want you to see here is that mid-ocean ridge is only one section of the plate. That's quite high. It's a little mountain range. It's actually quite a big mountain range underneath the ocean. The rest of the plate slopes away and then it falls down, subducting under another plate. So you have this shape of a very high mountain range and the plate moving away and then going back down. I think it's pretty obvious to see that gravity plays a big role here. This is high. High things fall. They fall down because gravity is pulling them down. So gravity is one of the main causes of our number 2 theory, which is called ridge push and slab pull. And because you love them so much, I made you one more animation. Let's have a look. I might need to pause this one as we go through. Here we have our mid-ocean ridge, and that fills up with lava as the lava rises, and then it comes out to form pillow basalts. And it's hot, so I'm going to colour it in red. Here is the rest of the oceanic plate, and there you can see that it's subducting under our continental plate at a subduction zone. Now over here the plate is already being pushed under, and it's cold because it's cold underneath the ocean. All of the heat that this plate has built up over here, that's all been leached out, and now the plate is quite cold over here where it's the oldest. I'm going to continue on the video. Okay, that happened a bit quick. Let's go back and have a look. That cold section of the plate is more dense, therefore it is sinking. This hot section of the plate over here is less dense, and that's why it's quite high and it forms mountains. The high slopes down to the low, which is also cold. In summary, in summary, sinking equals a pulling force. The cold equals a sinking force. So down on that right-hand side where everything is blue, the slab of the plate is pulling the rest of the plate down. Up here on the red side, the ridge is pushing up because of the lava, and the lava is hot, which is causing it to rise. So you have on the left-hand side a whole lot of red, and that ridge is a push. Therefore, we call this theory ridge push and slab pull. Two reasons that we call them there. One to do with gravity. Gravity is quite high and it causes things to sink. And number two, due to density. One side of the plate is hot and high, and it's pushing up. The other side of the plate is cold and sinking down. Summary. Theory number two, ridge push, slab pull. One side of the coin, the mid-ocean ridges are hot, therefore they're less dense, and therefore they are higher. They are pushed by upwelling magma, therefore this section here is called ridge push. On the other side we have the slab pull. The old oceanic crust is colder, making it more dense. Because it's more dense, it subducts under continental crust anyway. It is low in terms of the rest of the earth layers. It's sinking down into the asthenosphere. Because it's low, because it's dense, it pulls the rest of the slab, and that whole thing gets pulled down that direction. And that's why the second part of the theory is called slab pull. Altogether, we call this ridge push and slab pull. Lastly, it's important to note that this is underpinned by the force of gravity, which is pulling things down, and by density, which causes things to be pulled down. Okay, guys and girls, you need to go back and make whatever notes you need to remember this stuff. If you're to be successful, you get this in an exam, it will ask you to explain one or both theories explaining how continental plates move. You may need to draw a diagram, you may need to interpret a diagram, and the mid-ocean ridge one is particularly important as you go into Year 12 anyway. Here's what you can do for me right now. 1. Make yourself a title, today's date, make me a diagram of the layers of the Earth showing me the asthenosphere and oceanic and continental crust. 2. Subheading, convection currents. Draw me a diagram and give me a written description of what happens and why it happens. You can go back and rewatch that section of the video. I'll write that down there as describe and explain. Describe what happens, and then explain is why it happens, why the convection currents go around and why that causes the plates to go around. Another subheading there, number 2, was going to be ridge push, slab pull. Again, go through, give me a diagram, give me a description of what happens at the ridge and the slab side, and explain why that happens. Hint, it's because of gravity and density. I'm going to make sure we have a test on this one. All of these diagrams are really important, and you're going to be successful when you can explain why both of those theories illustrate how continental plates move. Good job, team. I'll see you soon.